Hello and welcome to my Chapter 10 rotational motion presentation, Part A, which deals with torque. So we imagine, as we were talking about in class, that we are exerting a torque on the door of the classroom or some similar door. In this case, the door opens the opposite direction, so in the picture I have shown. So we've got a force F that's going to cause a negative rotation about the z-axis. So here the z-axis is coming out of the page toward us, as you can see. And this force we can write as Fj hat because the force points in the positive y direction. So with force vectors, we define them based on the direction that they cause translational or linear movement in. Whereas torque vectors or rotational vectors, we define those by axis about which they cause rotation. Okay, so we talked about that last class. So in this case, force is Fj hat in the y direction. And that force is going to cause the door to rotate about the negative z-axis. And so at some point later in the motion, we see that the door is going to be at an angle. And the force at this point is no longer at a 90-degree angle to the door surface. Instead, it's at some lesser angle, as you can see. Also, if we move the force, or if we try to push on the door, say, toward the middle, we're going to need a larger force to cause the same rotation. And that should be intuitive. And this is why people would not normally push on the middle of a door. So what we're talking about here is putting a force on the door handle to cause rotation. And so we have a few quantities to define to come up with an equation that we can use for torque problems, and that's what we're going to do here. Notice here that not all of the force contributes to the rotation. Only the force that's perpendicular to the door is going to cause rotation. And so that force is drawn here in purple as F perpendicular. And this is another vector that we can use trigonometry to solve for. If we know what F is, we can solve for F perpendicular, given angles. So now we're going to calculate torque as a vector quantity. The first thing we need to define and draw is something called the lever arm. So whenever we're dealing with torques, we need to know what is the lever arm associated with the torque. And the lever arm has a couple qualities. One, it points out from the axis of rotation. This is going to be important because we're dealing with vector quantities. So it matters if the lever arm points outward or inward. So for torque, we're dealing with the r vector for lever arm. And the r vector points outward from the point of rotation to where the force makes contact. So in this case, it has magnitude equal to the length of the door shown, which actually, if you're looking at the door from the front, this would be the width of the door. And so I'm showing here the r vector pointing out from the axis of rotation, which is basically out from the hinges, and ending at where the force is being applied. And now we can move the force vector over, because recall, we can move vectors in space as long as we hold the angle constant and hold the magnitude constant. So all I've done here is moved that perpendicular vector and the force vector F over, so that we can do some trigonometry and come up with an equation. Now we need to define the angle between the r vector and the f vector. And here we're going to call that angle theta. And at this point we have our vectors defined. We have perpendicular force F, perpendicular, in yellow, in purple, and we can define that based on trigonometry here. We see that that perpendicular vector is opposite the angle, and so Sine gives us opposite over hypotenuse. In this case, the hypotenuse is the original F vector, and the opposite side is the perpendicular vector. Now we're going to define torque as the product of the lever arm and the perpendicular force. So if we knew the magnitude of that perpendicular force, F perpendicular, and we knew the magnitude of R, we simply multiply them together to get the torque as a magnitude. If we're only given the actual force and not perpendicular force, then we need to take the sine of the angle. So torque is equal to R times F sine angle. Now if you take a look at these two vectors, and we look at the angle between them, and we look at the equation, we see that the magnitude and the angle of the torque are equal to that of a cross product between the two vectors. And so we're going to define torque as lever arm vector cross force vector, R cross F. And we see if we put our fingers in the direction of the R vector and we wave them toward the F vector, we get an axis pointing inward. And that means that the torque is going to point inward. And that's exactly what we want. And that gives us negative z as expected. So now we're dealing with superposition of torques as well in this slide. We can add torques together as vectors just like we can add force vectors together. So if one person is pushing on a table, for instance, to the right, and then another person is pushing on a table to the left, given the two forces, we can sum them together to determine the acceleration of that table or a cart or any kind of object. We've done that before in the translational motion direction, say like along the x-axis. We could do the same thing with torque. So if one person is trying to rotate an object clockwise and another person's trying to rotate that same object counterclockwise, we can add their torques together. And the way we do this is the sum of the torques is equal to each individual torque as a vector quantity, and then sum together. So this example here shows a wheel that has an outer handle and an inner handle. So the inner handle is located at radius 1. The outer handle is located at radius 2, which is the outer edge. And one person is exerting a force F1 on the inner handle, and another person is exerting a force F2 on the outer handle. And so we're also going to define our axis, z-axis, as pointing into the page here. And so now we can define torque directions. So what's going to happen when F1 exerts the force at that radius R1? We can see that that's going to cause counterclockwise rotation of this object. And if we put our thumb in the direction of the z-axis pointing into the page, positive rotation would be clockwise rotation here. In this case, F1 is causing counterclockwise rotation, so that torque is going to be negative. And F2 is going to cause clockwise rotation, so F2, that torque resulting from F2 is positive. And so we can say that the net torque is equal to R2 F2 minus R1 F1 K hat. And so we're keeping track of direction of torques and actual magnitude of torque. And notice here we don't need to use the sine term because these F vectors are already at perpendicular 90-degree angles to the radii. So hopefully you've followed each thing that I've talked about in this presentation. Now what we're going to do is go over two quick examples to solidify the concepts. So the first example is taken from OpenStax problem 1071. We've got two flywheels. We neglect the masses of the flywheels for now. And they have different radii. And they're bonded together so they rotate about a common axle. The smaller flywheel has radius 30 centimeters, and there's a cord pulling on it with 50 newtons as shown. What pulling force needs to be applied to the cord connected to the larger flywheel of radius 50 centimeters so that the combination does not rotate? So what I'm doing here is drawing the vectors themselves that show the lever arms here, because we have F1 at a distance R1 and F2 at a distance R2. And notice that these force vectors now make 90-degree angles to the radii. And so what we're given now, if we look at it in terms of the variables that I've defined, F1 is 50 newtons, R1 is 0.3 meters or 30 centimeters, R2 is 0.5 meters, and the quantity that we're trying to solve for is F2, such that this whole apparatus does not rotate. So if the torque caused by F2 is greater than or less than the torque caused by F1, this apparatus is going to rotate. So intuitively, you should see that. Later on in further lectures, we're going to talk about why that is and how come the torque balance has to happen. But for now, we can see that we want these two torques, F1 and F2, to balance each other. So the question is, what is F2 so that net torque is 0 for no rotation? And the observations that we see here is that forces make 90-degree angles with the lever arm vector, so we don't need sine theta. And that if we set up the x-axis as shown, pointing into the page, now we can start to define positive and negative vectors. So we can see here that the calculation is R1 F1 positive minus R2 F2 negative gives us our net torque, and they're all along the I-hat direction. So hopefully this makes sense that F1 is going to cause positive rotation, so that R1 F1 torque has to be positive, and F2 is going to cause negative rotation, so that R2 F2 has to be negative torque. So this equation seems correct. And using this equation, we see that in order to get 0 net torque, we have to set R1 F1 equal to R2 F2. And so plugging in numbers here, we see that F1 has to have a magnitude of 83.3 newtons in order for that to happen. Now let's take a look at another example. So here we're given a drawbridge, and it's known that a torque of 5 times 10 to the 3, or 5,000 newton meters, is required to raise the drawbridge. What is the necessary tension to produce this torque? So we can see the tension force acts at a 30-degree angle. We can see the drawbridge is going to pivot on the left side there about the origin. So looking at the axis system that I drew, we've got Y and Z. So the first question is, about which axis will the drawbridge rotate? And we can see that this drawbridge rotates in the plane of the page, so it rotates about an axis going into or out of the page. We don't know which direction yet, but we know that it's into and out of the page. And so that has to be the x-axis. And so what is the direction of this x-axis? Well, it's got to be either into or out of the page. So now we have to use a right-hand rule. So if x is pointing into the page, we put our fingers along that x-axis into the page. We wave them to the y-axis, and our thumb gives us a direction of the z-axis. And so that makes sense. So that means that x has to be pointed into the page. So another question that we could ask is, will this tension cause a positive or negative rotation about that x-axis? And we can see here that positive rotation would be clockwise motion because x goes into the page. So put your thumb in the direction of the axis. Your fingers curl around the direction of positive rotation. So in this case, the tension force is going to cause negative rotation about x. So what are we given here? So the given quantities are required torque is 5 times 10 to the 3 Newton meters. We know that tau is equal to R cross F. And here, F is the tension force as shown. So I've drawn a vector now over top of that that shows F as the tension force. And R is the lever vector that I have drawn here in purple. So we've got our lever arm vector R, we've got our force vector F, and we've got the angle between them so far shown as 30 degrees. We know that R is 6 meters. And so now we don't need the picture anymore. But in order to take the cross product, these vectors have to be tail to tail. We can't do a cross product like this. So we need to move the F vector over. And so now we move it over, and we see that that 30-degree angle is not the correct angle between these two vectors. So instead, we're looking for the angle between the two, and that is the 150-degree leftover angle from these two supplementary angles. And now we can get rid of the 30-degree angle, and we know that we've got two vectors, F, which we're trying to solve for, and R, which is 6 meters, and the angle 150 degrees between them. And we know that the required torque has to equal 5,000 Newton meters. So 5,000 Newton meters is equal to magnitude of R, magnitude of F, sine phi, which is the angle between them. And plugging numbers in here, we've got 5,000 Newton meters is equal to 6 sine 150 times F. And now rearranging the numbers gives 5,000 over 6 sine 150. But sine 150 is 0.5, and so we've got 5,000 divided by 6 times 0.5, which is 5,000 divided by 3 to give our final answer. Hopefully you've learned something about torque in this presentation. Be sure to practice the in-class assignment, Chapter 10, to get more practice with torque, the right-hand rule associated with torque, and axis system right-hand rules. Thanks for watching.